Hamming code uses multiple parity bits. It can detect and correct error bits. A Hamming code with n parity bits can have up to 2 power n minus 1 data bits, making a maximum code length of 2 power n minus 1 bits. So the table shows us how many parity bits and how many data bits and the total bits used in the Hamming code. For example, if the number of parity bits in the Hamming code is n is equal to 3, then the data bits used will be 2 power n minus 1, that is 2 power 3 minus 3 minus 1, that is equal to 4. So for the number of parity bit n, that is 3, the total the data bits in the Hamming code will be 4, and the total bits or the total length of the Hamming code will be the number of parity bits plus number of data bits. So that is 3 plus 4, so that is equal to 7. So in this way you can find out the number of parity bits used in the Hamming code, then the total length of the Hamming codes, and the number of data bits in the Hamming code. Now we are going to see in a Hamming code in which position the parity bits are used and in which position the data bits are used. So the parity bits are used in position 2 power I. So 2 power I means I represent 0, 1, 2, so on. So 2 power I means 2 power, now consider I is 0, 2 power 0 is 1, and 2 power 1 is 2, and 2 power 2 is 4, 2 power 3 is 8, and so on. So in the position 1, 2, 4, 8, 16, 32, and so on, the parity bits are used. And in the data bits are used in the remaining positions, that is in 3, 5, 6, 7, 9, and so on, the data bits are used. So here now we'll see in which position we have to write the parity and data bits. So for example, consider the Hamming code is of has length 15, the bit positions are of 15 positions are there, and the length of the code is 15. So we'll now write in which position the parity bits will come and in which position the data bits will be used. So here in bit position 1, the parity bit will come, so P1. So here we saw in position 1, position 2, and so on, 4, and so on, the parity bit will come. So P1 will come here and P2 in position 2, and in third position the data will come. See here 3, 5, 6, and so on, the data will come. So the data bit will come, so D3, and in fourth position parity bit, so P4, fifth is data, sixth is data, and seventh is also data bit, and in eighth parity, ninth is data, 10th is also data bit, 12th also data bit, 13 is data bit, 14 is also data bit, 15 is also data bit. So in this we have used 4 parity bits and the rest is data bits. So in this way we can frame the Hamming code. Let us consider Hamming code generation with an example. Consider a 5-bit data 11010. So using even parity, we are going to use Hamming code to code this data. So even parity is used. So the position of this bits is of this data bits is, so as I discussed earlier, so the data will be, the position of this data will be, the position of this will be 3, this is 5, 6, 7 and 9. So the the parity will be, the position of the parity will be 1, 2, 4 and 8. So from this, you know, the length of the Hamming code will be a 9-bit. So here in the position 1 we will have the parity P1, position 2 parity P2, then here the data D3, then the parity P4, data D5, data D6, data D7, here the 8th is parity P8 and D9. So next we have to find the, we know the datas are 1, 1, 0, 1, 0. We know the data, that is this one. Data is known, only we have to find the 4 parities. So to find the parity, so here P1 can be found by XOR of some data bits. So you have to XOR some data bits to find P1. So we have to know which data bits we have to choose to find P1. So for that, let's refer this table, use this table to find. So here the 9 bits position, that is 1 to 9 I have written, and the equivalent binary bits also is written in the table. So in this, the first position is for parity and second also parity, third is for data, fourth is of parity, fifth is data, sixth, seventh is also data, eighth is parity, ninth is data. Okay, next, so we have to choose the data bits to find the parity 1. So this is the positional weight of this binary is 1, 2, 4 and 8. So now we are going to choose for parity 1. So for parity 1, the first position, the first bit in the binary number should be 1. So the bits, the first binary bit should be 1. So here, and we should also only choose the data, in the data bits, in the data which are the first binary bit is 1, we have to see, only from the datas we have to see. So here we know in D3 the first binary bit is, you can see here, is 1, and also in D5 the first binary bit is 1, and D6 first binary bit is 1, and also D9. So we have to choose from D3, D5, sorry, this is D7, okay, D7 and D9. So here, so this is equal to XOR of, so what is the value of D3? So here D3 is, from this you have to find. So D3 is 1, then D5 is 1, D6 is 0, D7 is 1 and D9 is 0. So we have the left, in the position 1, 2, 4 and 8 we have to find the parity. So in D3 1 is there, then D5 1 is there, and D7 1 is there, and D9 is 0. So the answer will be, you know, the XOR, the operation is odd number of ones is there, means the output will be 1. So here odd number of 1, so output is 1. So P1 is now 1. So you can write the value P1 1 here. Next we have to find P2. 2. So P2 is XOR of some data bits. So we have to find the data bit. So we have to check in the second position wherever the data bits in the second position where there is 1. So in the data bits in the second position, see in D3 it is 1 is there, D6 1 is there, D7 1 is there. So D3, D6 and D7. So D3, D6 and D7. So that is equal to XOR of, so D3 is 1. So here D3 is 1 as per this. Then D6 is 0 and D7 is 1. So even number of 1, so the output is 0. So P2 is 0. Then P3. So XOR of, so we have to check, sorry, P4. So we have to check the fourth positional weight, that is this one. So here that is the third bit should be 1. So here in this D5 third bit is 1, D6 1 third bit, D7 third bit is 1. So D5, D6, D7. So that is equal to XOR of, so D5 is 1. So D5 is 1, D6 is 0 and D7 is 1. So even number of ones and output is 0. So P4 is 0. Then P8. So XOR of, so we have to take the 8th positional weight. So the fourth bit should be 1. So in only from the data bit we have to choose. So here D9, we should not choose from the parity bit, only from the data bit, that is here D9 only will come. So D9, so that is equal to, so XOR of D9 is 0. So that is equal to 0. So even number of ones. So here put 0. So these are the parity bit. And the other is data bit. So the Hamming code is 1 0 1 0 1 0 1 0 0. So this is the answer. That is, this is the Hamming code that we have found. This is the Hamming code for the data 11010. So this generated Hamming code is now sent as a message to the receiver, and the receiver will check whether there is any error in it. So how it does it is by finding check bits. So the check bit, here we find 4 check bits. Since there is 4 parity bit we used in this code, Hamming code, it finds 4 check bits, that is C1 is equal to XOR of, so here it uses the parity bit 1 and also it uses the datas from this P1, that is D3, D5, D7 and D9 it uses. So P1 it includes the parity bit P1 and the data bit D3, D5, D7 and D9, and it finds the XOR of these things. So XOR of P1, here this represent P1, this is P2, D3, P4, D5, D6, D7, this is P8, this is D9. So P1 is 1, D3 is 1, D5 is 1, D7 is 1 and D9 is 0. So C1 is equal to 0 because its even number of ones are present. So the OR XOR of even number of ones is the output is 0. Next is C2. So XOR of it includes P2. Then it takes the data bits from this P2, that is D3, D6 and D7. So D3, D6, D7. So that is equal to XOR of P2 is 0, D3 is 1, D6 is 0 and D7 is 1. So even number of 1, so output is 0. Then C3. Again XOR of it includes P4, C4. So P4 parity it includes. Then the data bits from P4 it includes D5, D6, D7. So it is D5, D6, D7. So that is equal to XOR of P4 is 0, D5 is 1, D6 is 0, D7 is 1. So even number of 1, so the output is 0. Next C8 XOR of it includes P8, the parity 8, then D9, that is from this one it takes the data from P8 it takes. So that is equal to XOR of P8 is 0, D9 is 0. So that is equal to 0. So here the check bit C is equal to C8, C4, C2 and C1. So here we have found C1, C2, C4 and C8 we have found. So here C can be written as C8 is 0, C4 is 0, C2 is 0 and C1 is 0. So 0, 0, 0, 0, 0, 0, 0, 0 means we can conclude that there is no error in the message that is sent. The message that is received, the Hamming code that is received in the receiver, there is no error. Suppose this is the message that is sent by the sender to the receiver, but the receiver receives this message. You can see there is a change in this bit. Here it is 0, this is changed to 1, so there is an error. So now Hamming code is can help us to is used to detect errors, and also we can correct the errors using Hamming code. So we use the check bits to find the error in the message that is received. So this is the received message. So we are going to now use the check bits to find the whether there is any error in this message. So here we can just label it. This is P1, P2, D3, D4, D5, sorry, this is P4, D6, D7, P8 and D9. So here C1 let's find. C1 is equal to XOR of, so P1 is 1 and D3 is 1 and D5 is 1 and D7 is 1 and D9 is 0. So that is equal to 0 because even number of ones. Then C2 is equal to XOR of, then P2 is 0, D3 is 1 and D6 is 1, D7 is 1. So odd number of 1. So the check bit C2 is 1. So here again XOR is P4 is 0, D5 is 1 and D6 is 1 and D7 is 1. So again odd number of 1. So the output is 1. Then C8 XOR of P8 is 0 and D9 is 0. So output is 0, even number of ones. So now C is equal to, check bit C is equal to C8, C4, C2 and C1. So C is equal to C8 is 0 here. This is C4, so 1, then C2 1, then C1 is 0. So C is equal to 0, 1, 1, 0. So when you convert this into decimal, in decimal this is 6. The decimal of this is, equivalent of this is 6. So from this you can understand in bit 6, bit position 6, there is a error. So here in bit position 6. So where is 6? This is the 6th position. This is the 6th position. So in this there is a error. So now the error has been detected. So here, so next you can change the, correct the error from 1 to, you can make it 0. And so in this way you can find the error. Suppose if, for example, if C is equal to 0, 0, 1, 0 means if you get, that is, this is a C8, C4, C2 and C1. Suppose for example if you get this for as a check bit, means the decimal equivalent of this is 2. So there is a error in bit 2. Bit 2 there is a error. So like this you can find out. Suppose for example if the check bit is 0, 1, 0, 0 means, you know, in bit 4 there is a error. So you can correct it. You can, so in this way error detection can be done.